Hi everyone, and welcome back to another AP Calculus video. Today we're going to continue our discussion of finding volumes of solids. And today, instead of having a shape like a square or a triangle or a semicircle plop down onto a flat base, now we're going to talk about what happens when we have a curve that just gets revolved completely around an axis. And so here, as we think about what this might look like, consider like a table leg or a chair leg. One that's round and kind of maybe has those decorative, ornate things. It's been spun on a lathe. And that's kind of what we have going on here. So if we have this curve that's given by this function stated here, and we revolve it around the x-axis, what happens is it creates this kind of mirror image down below, and you get kind of this nice looking table leg. And if we were to take and slice it whoosh, right there and turn it and open it up so you could see, hopefully in your mind's eye, you can see that the cross section would be a circle. And everywhere along you'd have a circle. Sometimes the circle would have a smaller radius, sometimes it would be a larger radius. And so as you're spinning it, you get this circular cross section here, and the radius of the circle is just the y value, the distance from the x-axis up to the curve. Anytime it's a distance from an axis to a curve, it's just going to be the function itself. So if it's from the x-axis, it's a function of x. If it comes from the y-axis, which we will see, then it's a function of y. So it really depends on where we're perpendicular to. So here my circles are perpendicular to the x-axis. That's another indication that it's a function of x. If your cross sections are ever perpendicular to the y-axis, then it would be a function of y, just like we saw in our introduction. So really, we're going to take the same approach to solving these as we did with the solids that have the flat base. So we're going to find an area function. Here, it's just going to be a circle. So instead of a square or a triangle or a semicircle, it's a full-on circle. So our area function, anytime we're revolving around something, when you revolve, it makes a circle. So our area function is going to be pi r squared. It's just a circle. It's an area of a circle. Now we're going to treat it the same way that we did yesterday. We're still going to consider dx, or sometimes in some cases dy. Dx is the width. So as I measure the thickness of the circle, am I measuring it along the x-axis or the y-axis? And that's another way to kind of decide, oh, is it dx or dy? So here, the thickness of my circle is a measurement of x. So we say it's a dx. It's also perpendicular to the x-axis, so it's dx. So this is what we're going to do today, and we're going to discuss how to set these problems up. So let's go ahead and figure it out. So our area function is simply pi r squared. So what is r? Well, looking at my graph, r goes from the x-axis up. It doesn't always go from an axis. Sometimes r goes from a different line. So we have to really pay attention and understand what's happening. So the first thing I do is I sketch a mirror image down below the axis of revolution. So that's what we call this. It's the x-axis is our axis of rotation or revolution. Okay, so the axis of rotation here is the x-axis. We're going to see very soon that sometimes it's a line and it's not always the x-axis. So here, that's our axis of rotation. So I'm going to label that, and I always label it with this little rotatey thing. And I always like to sketch in a little dashed line for my axis of rotation. So I'm going to go ahead and do that, mark the x-axis, because again, sometimes it's not an axis, and your axes are always going to be drawn with solid lines. So it's always a good practice to label your axis of rotation with a dashed line. So dashed line. All right, so now that we have our axis of rotation, we've got our label there, we know it's a dx setup. Now I'm going to mark where I'm starting and stopping. So from -2 to 2, this is what I want to find. So those are also going to serve as my limits of integration as I set this up. And so basically I'm ready to go. My radius is the function itself, so it's the equation. It's this y distance. So it's the 2 plus x cosine of x, the function given in the problem. So that's nice and easy. So let's go ahead and set that up. So the area for a disk, and that's kind of what we're calling this, it looks like a circular disk. the area, it's going to be integrated, whoops, let's do that down here. From -2 to 2, it's going to be pi times the radius. Okay, let's get the function. So it was 2 plus x cosine x squared. 2 pi r squared dx. This is my integral. And now we could plug it into our equation or plug it into our calculator and evaluate this integral. We could use our tricks about, plugging it into y1 and evaluating it that way. There's lots of little shortcuts that we could use. I'm just going to go ahead and plug it in. Math 9, -2 to 2. And then we don't forget about pi r squared. So 2 plus x cosine x, close my parentheses, squared, dx. Make sure I'm not squaring pi accidentally. And there's my answer, 52.42, and we'll round it to 9. There we go. So this is our process. It's, again, coming back to the idea that when we are doing these problems, it's just the area function times dx or times dy. So it's either a function of x or a function of y. So let's see some more. So here we've got a solid generated by revolving a region in quadrant 1, bounded by y equals x squared, y equals 0, and x equals 2. Okay, so let's make a little sketch. Y equals x squared looks like this. Okay, y equals 0 and x equals 2. So x equals 2 is going to kind of be a line like this. This is x equals 2. And then y equals 0 is just the x-axis. So we're revolving the area in quadrant 1 bounded by these 3 curves. So that's this area right here. Okay, we're going to take that and we're going to revolve it around the x-axis. So I'm going to label my axis of revolution. I'm not going to draw the dashed lines in. I think it would be a little too much. But this is what we're going to be revolving. So we're going to integrate from 0 to 2. So 0 is where that blue graph, y equals x squared, crosses the x-axis. That's easy to figure out. Make sure you're confirming things algebraically if your functions are not obvious, like I feel like these are fairly obvious to see that this is in fact 0. So we know we're going to integrate from 0 to 2. We also know that since we're revolving around the x-axis, this is going to be a dx setup. So in our picture, we're always going to make a note, oh, it's dx. We're perpendicular to x, it's dx. So since we're revolving, I'm going to go ahead and make a little mirror image. We'll do this with rainbow. There's my mirror image, and when I slice it, I'm going to have these circular discs sliced all the way through. So this would make kind of like a volcano shape once we were done. So let's identify the area function. Well, the area function is going to be pi r squared. So let's figure out what r is. R is the distance from the x-axis to the blue curve. So if I zoom in, this is r right here. So this slice is like looking at a quarter, and then you turn the quarter, right? And to figure out the radius. So this distance here, this is my radius. Well, the radius is the y value. It's the y function. So what is y? Well, y is x squared. So r equals x squared. So now there's my radius. So my function is pi times x squared squared. There's my area function. That's easy. Now I just plop it into my integral. I knew I was going to integrate from 0 to 2. We said that. So pi times x squared squared dx. Now I'm going to integrate this one by hand because this one is an easy enough one. So this becomes pi x to the 5th over 5 from 0 to 2. So 32 pi over 5 is the area, or the volume, cubic units, whatever they are, of this like volcano-shaped, cone-looking whatever object we get from revolving this particular shape around that x-axis. So all in all, remember, it's all about the slicing, right? It's going to be a circular disc. Every time it's a circle with these, anytime you're revolving, it's a circle. It's just a matter of, is it dx or is it dy? And it all has to do with what am I perpendicular to when I slice. So let's take a look at an example like this. A solid is generated by revolving the region bounded by x equals square root of 5 y squared, and x equals 0 and y equals -1 and y equals 1 about the y-axis. Find the volume. So let's make a sketch. Okay, here we go. So to sketch this, I kind of need to, so x equals y squared. This is a sideways parabola. So I kind of need to know this. Anytime you have things that are squared and it's opening this way, okay, and I'm x equals 0, that's this. So I'm going to label my axes x and y. X equals 0 is the y-axis. Y equals -1. And y equals +1. X, y equals 1. And we're revolving. So the region bounded by this curve, these lines, so it's this region right here. Craziness. Okay. And we're going to revolve around the y-axis. So this problem is going to give me like an hourglass looking shape. So as I revolve it around, so let's look at our cross section. So we'll use a little rainbow pen. That's kind of fun. There we go, rainbow. There we go. And so there's my cross section. So as I'm labeling, ooh, this time I'm perpendicular to the y-axis. So this is going to be a dy setup, which is nice because I have x equals for a lot of my things. So this is a dy setup. And so my circular discs are like this, and when I flip them up, that's when I see the circle. So now let's figure out a of x. It's pi r squared. But what is r? Well, r is this distance here. R is, it's x, right? So I'm going left and right. So it's x, and it's this sideways parabola. So it's this. So r is x equals square root of 5 y squared. Okay, so this is my radius. So I'm going to set this up, and it's going to be a dy setup. And I'm going to integrate from y value to y value. So now my limits of integration are also going to be the y numbers. So here I'm going to go from -1 to 1. So when I set up my integral, -1 to 1 pi, and then r is square root of 5 y squared dy. Now I can also integrate this one by hand. When I square everything, I get 5 pi y to the 4th dy, so that's y to the pi y to the 5th, and when you divide by the 5 it cancels out, so from -1 to 1, so we get pi minus -1 pi, so plus a plus, oh, it's 2 pi. There we go, and we can confirm it in our calculator using Math 9 to evaluate the integrals, but I want to make sure that we're good at doing this by hand as well. So again, we knew this was a dy setup because when we made our sketch, our cross section was perpendicular to the y-axis. So let's keep going. Let's see another example. The volume of a solid generated by revolving the region in quadrant 1, bounded by y equals x squared, y equals 0, and x equals 2, about the line x equals 2. So this is what we're finding the volume of. So let's make a little sketch. Okay. So we're only in quadrant 1, so let's do this. Okay, so y equals x squared, oh, that's easy. Okay, that's that one. Y equals 0, that's the x-axis. Okay, so I'm going to label my axes here, x, y. Y equals 0, x equals 2. So this is x equals 2. Oh, and we're revolving around x equals 2. So I'm going to label that. And sometimes I'll label it with a dashed line, but here it's one of my boundaries. So the area in quadrant 1 here gets revolved this way. Weird. It's not around an axis. So, okay, well, let's approach it like we normally would. So I'm revolving this way, so my cross sections, ooh, they're perpendicular to the y-axis, so it's going to be dy set up. And now my radius, ooh, this is my radius here, so let's zoom in. This is r. So let's think about this. This is where it gets a little tricky. The distance from the y-axis to my axis of revolution is 2. The distance from the y-axis to the curve is y. Well, looking at this, y plus whatever r is should equal 2. So y plus r should make that whole distance, which means r equals 2 minus, oh, and that's x. It looked like a y. 2 minus x. So sometimes it's really tricky to figure out what the r is, and you really have to have a good handle on the geometry and setting up your problems. So here, r is 2 minus x. So to find my area function is pi r squared, but r is 2 minus x. So it's pi times 2 minus x squared. Now I can't leave it as x because it's a dy setup. So I have to figure out what x was. So if I go up here, y equals x squared, that means x is going to be the square root of y. So I'm going to change that out, square root of y, square root of y. And again, it has to be in terms of y because it's a dy setup. So up here, 2 minus the square root of y, because y was x squared, so x equals the square root of y. This is where this is coming from. So x is always the distance, but because it's a dy setup, I need to find x in terms of y. So now I'm ready to set up my integral and solve it. So let's do that. So putting everything in, here's my integral, and I know I'm going to go from 0, but then I need that upper limit of integration. So what I need to do is I need to come up here and I need to find this spot right here. So if I know x is 2, using my equation, y equals 2 squared, the y value there is 4. So I'm integrating from 0 to 4. So I have to find that y coordinate as well. dy, everything needs to be in terms of y. So at this point, I would plug it into my calculator and evaluate. You can do this by hand. You have to FOIL everything out, but let's use our calculator right now. So getting everything in there, here's our result. And remember not to square the pi, and remember not to leave it out. So pi r squared. And remember you're going to use x in the calculator and not y when it's a dy setup. So one of the toughest parts about finding these volumes is when we're revolving around axes, trying to find that value for that radius. So we saw two cases in this video so far. We saw the case where you're revolved around the x or the y axis. That's by far the easiest because r is just going to be f of x or some function of y depending on, if it's dx or dy. Now, the other case that we saw here was we had some function where we were revolving around something to the right. So axis of revolution is to the right. Then we saw that our answer here, and it can be to the right, or if we're in a dx setup, axis of revolution, it wouldn't be to the right, it would be above. So suppose we have, some function where we're revolving above. If our axis of revolution is above, well, then it's going to be basically the axis of revolution minus the function. If it's f of x, if it's in dx setup, or f of y if it's dy. So you had to take the axis and take away the function to get that length. Because remember, this is your axis of revolution, this is your function, this would be f of y. The radius you want is this piece that's left. So you have to take away the function from that axis of revolution. The same thing is true if we're above. So here's your axis of revolution. Here's your function. If what we want is this, if this is my radius as we're revolving up and around, well then we need to take away f of x from that whole distance. So something to wrap your brain around. So these are the two cases we saw. We didn't see an above, but the above is the same idea as to the right. It's greater than your function, right? Now the last case that we haven't seen that we'll see in a future video is what if your axis of revolution is below or to the left? And what that would look like is you have a function here, and here your axis of revolution is down here. So as you revolve around, the radius that you're going to look for is this function plus the axis of revolution. So if you're below or to the left and you're revolving over here, then what happens is this radius, you're going to add to it. So here's your axis of revolution, here's your function of y, right? So this would be a dy setup. So dy, this would be dx. And you would take that axis of revolution and you would add it. So axis of revolution plus f of x or f of y, depending on your setup. So you're going to add it because it becomes longer than the function, right? So that's the idea, and drawing pictures and thinking it through, this is kind of going to be the best way that you can troubleshoot and figure this out. But that's always a troubling thing for people, is trying to figure out the radius. There's really three cases. You're either the axis and it's the function. It is going to be shorter than the function, in which case you subtract the function, the axis of revolution minus the function, or it's going to be longer. That's axis of revolution plus the function. So those are your three basic cases for finding the radius, and if you put them into practice, you'll be successful every single time when you approach a problem like this. So it takes practice. You're not going to get it right away perfectly, and that's okay. It's a learning process. Stick with it. Do your homework. Do your practice. You can do this. You've got it.